As we gaze up into the night sky, countless twinkling lights captivate our imagination. But among these celestial bodies, some stars appear more radiant than others. What makes these stars so bright? How do they shine, and why do certain stars outshine the rest? In this exploration, we delve into the science behind star luminosity, focusing on the factors that contribute to the brightness of stars. Stars are not simply points of light. They are massive, luminous balls of gas, primarily composed of hydrogen and helium, that produce energy through nuclear fusion. The energy released during these fusion reactions manifests as light and heat, which is emitted into space. The brightness of a star, known scientifically as its luminosity, depends on several key factors: its size, temperature, distance from Earth, and intrinsic characteristics, like age and composition. A star's size plays a crucial role in determining its brightness. Larger stars have a greater surface area, allowing them to emit more energy. This is why giants like Betelgeuse and Antares, both classified as red supergiants, appear so bright in the night sky. These stars are many times the size of our Sun, and because of their vast size, they emit an enormous amount of light, even though they are cooler than smaller, hotter stars. However, size alone doesn't guarantee brightness. The star's surface temperature is another critical factor in determining how much energy it releases. Hotter stars like Sirius or Rigel are much smaller than red supergiants, but shine incredibly bright due to their higher temperatures. The hotter a star is, the more energy it radiates in the form of visible light. The relationship between a star's temperature and brightness is governed by the Stefan-Boltzmann law, which dictates that the total energy radiated by a black body is proportional to the fourth power of its temperature. Temperature influences both the color and the luminosity of a star. Stars with higher temperatures, such as Sirius, the brightest star in the night sky, appear bluish-white because they emit more energy in the blue and ultraviolet spectrum. These stars, known as O-type and B-type stars, can be several times hotter than the Sun, reaching temperatures exceeding 30,000 K. In contrast, cooler stars like red giants and dwarfs appear reddish. Despite being less hot, these stars often appear quite large and still shine brightly due to their massive size. This variation in temperature and size results in the diversity of brightness seen in the night sky. The apparent brightness of a star is also determined by its distance from Earth. A star that is closer to us will appear brighter than one that is farther away, even if both stars have the same intrinsic luminosity. The inverse square law governs this phenomenon. The brightness of a star decreases as the square of the distance from Earth. This is why stars like Sirius appear so bright, despite not being the largest or hottest. They are relatively close to us, at only 8.6 light-years away. In contrast, cooler stars like red giants and dwarfs appear reddish. Despite being less hot, these stars often appear quite large and still shine brightly due to their massive size. This variation in temperature and size results in the diversity of brightness seen in the night sky. The apparent brightness of a star is also determined by its distance from Earth. A star that is closer to us will appear brighter than one that is farther away, even if both stars have the same intrinsic luminosity. The inverse square law governs this phenomenon. The brightness of a star decreases as the square of the distance from Earth. This is why stars like Sirius appear so bright, despite not being the largest or hottest. They are relatively close to us, at only 8.6 light-years away. The chemical composition of a star is another crucial factor. Stars that have a higher proportion of heavier elements, known as metals in astrophysical terms, tend to be more efficient at producing energy, which can influence their brightness. These stars, which are often found in younger star clusters, shine more brightly than older stars that have fewer metals. While the brightness of stars is influenced by the aforementioned factors, Certain stars stand out due to their sheer brilliance or fascinating characteristics. Sirius, for example, is both the brightest star in the sky and a binary system, with its companion, Sirius B, being a white dwarf. Despite its small size, Sirius B contributes to the overall luminosity of the system, demonstrating how the interplay between multiple stars can affect the system's total brightness. Another example is Vega, one of the most prominent stars in the Summer Triangle. Vega, a white main sequence star, is similar to our Sun but significantly brighter due to its higher temperature. Its relatively close proximity to Earth also enhances its apparent brightness. Stars like Alpha Centauri A and B and Proxima Centauri offer additional examples of stars with varying luminosity based on their size, composition, and proximity to Earth. Alpha Centauri A is a yellow star similar to the Sun, but much brighter, while Proxima Centauri, the closest known star to Earth after the Sun, is a red dwarf that shines faintly compared to the larger stars. Stars shine with varying intensity due to an intricate combination of size, temperature, distance, and age. Some stars, like Sirius and Rigel, are bright because they are hot and relatively close to Earth, while others, like Betelgeuse, are enormous but cooler. Understanding the factors that influence stellar brightness helps us appreciate the complexity and beauty of the universe. Whether it's the fiery brilliance of a young, massive star or the faint glow of a distant red dwarf, each star has its own story of light to tell.